to create music that is semantically, rhythmically, and emotionally aligned with a given video. And it has many applications, like in film scoring, in games, in short video creation, in dance music synthesis, and so on. But this area is relatively underdeveloped because the relationship between the videos and the music are very complex, and there are actually a few industry deployment in this area. And in this figure below, we show some of the representative works in this area. Like in 2020 to 2022, there are some early methods like this MT and this Venus product from our team. These are the early methods, and these two methods are for the general video to music generation. And this Foley music and this the resolution is a little bit low, but this Foley music and this set sound is to generate music from a silent video. But this video is about a human playing an instrument, like playing a piano or a violin. And there also this dance to music and this rhythmic night. These two papers are it's about a video of like human dancing or human playing some sports, and try to generate a music that has that is aligned with this video in the local rhythm. So these are the early methods, and these methods are basically about symbolic music. And actually, most of the methods are about human movements, like playing instruments or human dancing or playing sports. But in the recent years, like in 2024, there are more methods about general video to music generation, and most of them are about audio form. Like there are some methods from universities from China and from America, from other countries, and also from some companies like Google or Adobe, or like some Chinese companies of Tencent or ByteDance. So the first part will be this overview of this video to music generation. So it's like we have we have 5 parts in this in this talk. The first part is the overview of this area, and then we'll discuss 3 papers of our team, and finally a very brief discussion on the social impact of this area. So this first part is basically based on this survey. The survey is from the last year's ISMIR is our survey on this video to music generation. So this figure is the overview of this area. We'll discuss the data sets and architecture and evaluation and challenges of video to music generation. And for the data sets, you can categorize these data sets by their input types or output types. And for the input types, the input can be general videos or motion videos. Motion videos can also be named as human movement videos. And there are also images. And for the output types, it can be symbolic music or audio music. And for the architecture, basically all of the methods in this area can be, you can understand it as 3 parts. The first part is video encoding, like you try to extract features from this video. And the second part is a projection module. It tries to map the feature of the video encoding into the music generation module. So finally, the music generation module tries to generate music. So the video encoding is basically with image models like clip or video models like video clip. And this projection module is sometimes the method may use this adapter, or they may directly use a text or the features as the bridge between these 2 modules. And this music generation is basically diffusion or autoregressive. And these 3 parts, they jointly models the video to music generation, models the video music relationships, which includes semantic and rhythm relationships. And for the evaluation can be categorized into music only and video music correspondence metrics. And you can also categorize it based on whether it is an objective metrics or subjective metrics. And for the challenges, there are many challenges like the standardized dataset benchmark, the customization, controllability, and the choice of symbolic and audio forms. We will discuss about these challenges later. So for the input, like we discussed before, there can be general videos or human movement videos or images. The general videos are basically like all the videos you found on YouTube can be like this, like natural landscapes, films, sports, animations. And for these videos, if you want to generate background music for this, you need to extract some semantic features like motion, color, or some other video semantics. But for human movement videos, which is like playing an instrument or the people dancing or playing sports, it's different. Like for instrument performance, like this. You can consider that this music is kind of determined by this video. Like it's more like a reconstruction. And for this dance videos, although this music is not determined, but they only emphasize on this local rhythm alignment. Because you only want the music to be like, if there's a strong motion in this video, you want a strong beat in this music. So this is the rhythmic alignment, but there are weak semantic constraints because you don't need the music to be like aligned with this video in the mood or in the style, in the genre, and so on. So like method in this human movement videos, they usually just use the 2D or 3D key points of a human motion as the representation of the input. And for the third input type is the images. For the images, because this image is static, then the music learns is like not determined by this input. Because for video to music, you can imagine the music has to have the same length as the input video. But for this image to music, the length is arbitrary. And also there are no local constraints, like you don't need to fit the tempo of the music or like the beats of the music with the video. But for the image to music, there may be less application scenarios. But one application I can think of is if you open your iPhone and you open the photo app, and you may find this function called memory, and it's just organize your images as an album, and it automatically creates a music for these images. So this may be one of the applications for this image to music. And for the output types, it's basically like the general music generation. It's either symbolic music or audio music. So the symbolic music is a sequence of discrete elements of notes, chords, or other music symbols. This is basically just MIDI events. And the early methods are about symbolic music because for symbolic music, you can integrate more music theory into this representation. Like you can explicitly define chords or beats in this representation, and because of this, you can have better controllability. And also, compared with audio music, the audio music the computational cost is very large because of the high sampling rate. But for the symbolic music, since this computational cost is relatively lower, so the music pieces can be longer. Like it can be 3 to 5 minutes, but for audio music, it's basically only 10 seconds. But there are some disadvantages of symbolic music. It's also like the general music generation. It's for symbolic music, there are only limited data scalability, because if you want symbolic music, you need to have this sheet music. And this can be difficult to obtain. And also it has weaker expressiveness. Because if you want to listen to this symbolic music, you need to like synthesize it into an audio with your sound sources or sound fonts. But this can limit the limited expressiveness of the music. But for audio music, you can directly generate the music end to end. So for audio music, the pros and cons are basically just the opposite of the symbolic music. The pros is you can have large-scale data sets and rich expressiveness, but the music just lacks the contributing and editing ability because it's end-to-end. You just input a text or video or image, and you generate the music. You cannot edit the music directly. You can only regenerate this music. And also because of the computational cost, the music pieces are a little bit long, not a little bit, very shorter than the symbolic music. Yeah, and this large table is about the methods in vision to music generation. So the first part is about general videos and images and as input, and the second part is human movement videos as input. So you can see the early methods like the first 4 or 5 rows are basically about no, the first 7 rows maybe about symbolic music generation, and from 2024 is most of the methods are audio. Yeah, but for this human movement videos, you can see although they are also generating music from videos, but this method is totally different because this video encoding is basically to the body key points. Yeah, and for the video encoding, the models can be a clip or some video models, and there are many choices. And for the music generation model, it can be autoregression, such as music gen, or some diffusion-based models like audio LDM or polyfusion. And for the data sets, it is also divided based on their input and output categories, and most of these methods are sourced from these music videos, and some are also from film videos or dance videos. And you can see that this MIDI-based data sets are usually they usually have smaller size than these audio data sets. Like this MIDI data set is usually only 1,000 samples, but for the audio data sets, it can be tens of thousands of samples. And these data sets also, they provide these annotations of like genre, like tempo, like chord key. It's basically either a text description or this music theory related metadata. And there are also some evaluation metrics. So for the objective music only metrics, the more commonly used ones are the FAD, FD, and KL. It's basically about computing the distance or similarity between 2 music pieces. And in this case, it's the ground truth music and the music you generate. And also for the these first 7 metrics, these metrics are like statistics of the music, of one music. So to use these metrics, you need to compute the statistics of the music you generate and the ground truth, and you compare them. And if they are closer, then your music is better. And also there are this beats coverage score and beats hit score. They're about the rhythm of this music. And for this video music correspondence, the most commonly used metrics are this image bind score or clef score. It's basically how to compute the similarity between 2 different modalities, like videos and audio. Yeah, there are also some other metrics defined by different papers, like this video music clip precision, which is our paper, and we will discuss it later. And for the subjective metrics, it's basically either you evaluate the music itself. If you evaluate the music itself, it can be the music melody, the rhythm, the richness, the audio quality, or you evaluate the region music correspondence. It's either the semantic consistency or rhythm consistency or emotion consistency. And there are also many challenges in this area. So for the first challenge is the lack of standardized data sets and benchmarks. It's like all of the models, all of the papers in this method, they just like develop their own data set, and they train their model on this data set, and they try to compare it with other methods trained on other data sets. So you can see it's not a very fair comparison. So actually we need a standardized data set for this. And also this metrics I introduced in this previous page, it's not very aligned with the preference of human. It's like if you have done this kind of research in this area, you may find that even though some music may have very low FD or very low FAD, but the music is not so good. And also for it's basically for all these objective metrics, they are not so aligned with human. But if you use the subjective metrics, the results is not easy to reproduce. So actually, I reviewed a lot of papers in this area, but to be honest, I don't believe in any of the experiment results. I just listen to their demos they provide, but the demos are always cherry-picked, so you still don't know whether their method is good or not. So it's like the main challenge in this area is that if you ask me which of this method is the SOTA method, I don't know, because there are no standardized benchmarks. Yeah. And the second is the limited customization and comparability. It's like we discussed before, most of the methods now are just audio. And some methods are symbolic, but of these methods, they cannot customize or control the generated music. It's always like you need to regenerate this music to get a better version of this music. Yeah, and this is also similar to this third challenge, which is the trade-off between symbolic and audio forms. And the fourth is the cross-domain generalization. It's like these methods are basically trained on some video domains, like music videos. But if you want to generalize this method on other video domains, such as this method trained on music videos, you want to do inference to generate music for film videos, then the music is totally a mess. It cannot generalize. Yeah. And this fifth challenge is actually from a friend of mine. He is a musician, and he suggests that there's currently limited human-in-the-loop feedback for iterative improvement. And because we want this method to be used by these musicians, like in the actual creation of film soundtracks, but if you want to achieve this, you need to have this human-in-the-loop feedback. Yeah, it's similar to this comparability challenge. And also there's the underutilization of large model capabilities, because there are like many applications of large models in text generation, in image generation, but for the music generation, we still haven't seen a GPT moment in this area. And the final challenge is the industry application challenges. It's like we have not seen many applications of this area in the industry. So the second part will be our initial attempt in the CMT, called CMT. It's in 2021. This is our paper in SM Multimedia 2021, and it's called Video Background Music Generation with Controllable Music Transformer. So it's a very early method. Yeah, there's some motivation. Before I introduce the motivation, to briefly introduce this paper, it's basically about generating a symbolic music. But since we do not have paired data set, for pair dataset, I mean that you have this dataset with some videos and their paired music, but we do not have these datasets. So we just design this rule-based method, or I should say the relationship between the videos and the music are rule-based. And and we only focus on the rhythmic relationships between the video and music. Okay, so to the motivation. And basically, there are many videos on this YouTube and other platforms. And if you want to create a music, it is very important for you to choose or generate a very suitable background music because it can like makes the content more memorable. But to create a video, you need to prepare video clips and pick some background music. And the most time-consuming part is you need to edit this video to fit the music because you want the music to fit this video frame by frame, and this can be very time-consuming. And there are also some copyright issues, like you do not want to use this copyright music. So our motivation or idea is to design a model to generate music from videos. Because back then there were no previous methods that have done this before. So this task is called video background music generation. But why don't we use retrieval? Because the generation can shorten the video production time, and it can also save a lot of copyright fees and meet the individual needs of people. And back then, these related works are not directly related to general video to music generation. Like this is the method I said before. It's trying to reconstruct the music from a silent video of a person playing a piano. And this is a music retrieval method. And there are also some general music generation methods, but they are not for video conditioned inputs. And some methods are from OpenAI because OpenAI were doing music generation back then, but not for now. But of these methods, they cannot generate a background music tailored to this particular or general video. So the key idea is we want to train this model to that the model can be trained with video and music and can generate music from a video as an inference. But the challenges of that time is we don't have sufficient pair data. And there are also very complex relations between the video and the music. So this leads to our core design. Is that we only train this model with music data. It's like we extract some music features from this music, and we use these features to train this model. This is for training. But for inference, we try to extract some video features from this video. And then these video features are converted into the music features. So in this way, at the inference time, you can just generate a music from video, but we do not need this pair data for training. Yes, this is the architecture of this method. The human defined relationships are these three rhythmic features we will discuss later. And the user can also define some specific features like genre and instruments. So for the three rhythmic relationships, the first one is the motion speed and the seminal density. This is based on this intuition that if the video has very fast motion, then you want the music to be intense, and vice versa. So for the music feature, we define this signal density. This signal density, we need to first define signal. So actually, signal is defined as the all the nodes that has this have the same onset time in a bar. Like in this figure, there are 5 nodes, but only 3 seminodes. And the signal density is the number of seminodes in this bar, which is 3 in this case. So our intuition is that the higher the signal density, the faster the local music rhythm. And to map the video features into the signal density, we use this optical flow. And we calculate the optical flow, average it over all of the frames of a video clip and define it as the motion speed. So the motion speed is mapped into the signal density. And the second one is the motion saliency and signal strength. This is another intuition that if this video have distinct motions, like there are transitions between some scenes, then you want this music to have distinctive music beats. So the strength is defined as the number of notes in a single note, which is 2 in this first single note. So the larger the strength, the richer and the more distinct the sound. And motion saliency is mapped into the single node strength. And motion saliency is defined by visual beats. Visual beats are the sound and decelerations, which is defined in this previous seed graph paper. So the third one is, the third relationship is we want to synchronize the opening and ending of a video and the music. We want the music to appear when the video starts. And we also want the music to disappear when the video ends. And if you want the music to appear when the video starts, it's very easy. But if you want the music to gradually disappear instead of just being cut off, then it is a little bit difficult. So our idea is that you need to inform the model that which segment the current music is in. Like, is it in the first % of this video or the last % of this video? So we designed this time encoding. It's like a kind of position encoding, but you tell the model like the specific time of this, a relative time of this current music piece. Yeah, and this comes to the representation of music. This representation is basically based on compound word transformer. And if you have read the paper, it's about a 2D representation of symbolic music. So we have 2 types of tokens. The first type is like this bar and beat, this 2 nodes, 2 tokens. It defines the start of a bar or a beat, and with the density of this bar or strength of this beat. And the second type of token is the node token. It just includes the duration, pitch, and instrument of this node. Yeah, so if we want to realize this controllable music generation, we just modify this density and strength in this bar or beat tokens. So the model will know that like if this density is 3, the model will know that I need to generate 3 similar nodes for this bar. And yeah, this is the overall framework. It's basically for training, we just try to reconstruct the music based on these music features, which is the user-defined features of genre and instruments, and also this similar density and strength. And for inference, we just extract this motion speed, motion saliency, and trying to convert it into the density and strength. And we use this data set called LPD, and it has 3,000 MIDI music pieces. Actually, the original data set is larger than that, but we only use 3,000 of this. And it has five instruments and 6 genres. And for the metrics in this paper, we just use the statistics-based metrics, like I introduced before, like you try to compute the pitch, histogram, entropy of the music, or other metrics, and then you compare these statistics of the music you generate and the ground truth music. And so this is the experiment results, and this table is for music generation without the video input, so it's without control. It's like even if our method do not have video input, and we only compare it with the baseline, we can find that it also has better music quality. This is partly because or define these strings can somehow achieve this plan before generation strategy. It's like you first plan that how many notes you want to generate for this beat, and then you generate these notes. So it makes the model more easier to learn. That previous experiment is about the music itself because we do not have video input. But for this subjective evaluation, it's for the video to music generation because back then we do not have any subjective metrics, any objective metrics for video to music generation. So we had to do this user study. We just hand out questionnaire to 36 participants, and we have like some videos, and for each video we have some music generated by our model and some music generated by baseline, and we try to compare them. Actually, the users just try to rank these models. So this baseline is the music generated without control, like without the video input. And this matched, it is a music that we select from a music database. So it's basically like a retrieval-based method. And we find that in terms of melodiness, it's the music itself. Our method is better than baseline, and it is close to the match music. And we think this is quite good because the match music is actually from the data sets. So the matched music is actually composed by human. And in terms of the compatibility, like the correspondence with the video, our generated music is much better. So this is the first demo of this of our method. And when you listen to this demo, please notice that when there are some strong motions in this video, please notice the change of music rhythm. Yeah, so this demo is basically about a carefully edited video, like a vlog. But the second video is actually shot by myself. It's a short video. Actually, it's shot at the Space Needle in Seattle, and it's only like 20 seconds. Yeah, so this is the first what I introduce is the first method. Oh, really? I choose this. Excuse me for a moment. Oh yeah, I see this. Shall I just replay this video? Hmm?
Maybe the second one, which is
Yeah, I think I can play this for maybe a little bit. Sorry. Okay, and the second one. Um, yeah, so this method is actually the first method for video background music generation, and we try to establish some rhythmic relations between the video and the music. And we designed this controllable music generation model that can be trained without paired dataset. And it can generate impressive results. So the second method, second paper I introduced is our paper in 2023. It's basically we want to address the problems in the first paper. It's basically that we do not have a paired data set for this area, and we do not have an objective metric for video to music correspondence. So in this paper, we first design this data set, and we design a method, and we also create an evaluation metric for this. So the data set is basically we try to decouple the melody, accompaniment, and chord in this music. And because for piano music, you can always extract the melody and accompaniment, and for the accompaniment, you can extract chords from it. So, and for the data set, we also try to extract this different parts of this music. So we crawl some music performance audio from this music videos, and we convert this audio into MIDI by this music transcription models, and we construct this video MIDI pairs. And we also provide other metadata like the tempo, the genre, the lyrics, and other music theory knowledge. And so this is the chord distribution among different genres. This is the rhythm distribution among these genres. For example, for the mandol pop, the tempo, the BPM is typically relatively lower, but for dance music and dance videos, the rhythm is the BPM is usually larger. And for the method, we designed this method that tries to disentangle the chord and melody and accompaniment. So we first try to synthesize a chord sequence from this video. And then we try to generate a melody based on this chord and generate an accompaniment from this melody and chord. And this is quite similar to how a musician creates a music. And so you first have this chord progression, and then you write this melody and accompaniment. Yeah, so we just extract many video features from this video to control the different stages of this music generation process. And this music representation is also a 2D representation based on the previous one. But the main difference is that we refine this representation, that we add this two representation of chords. The first is the root quality. It's like for the C major chord, the root is C and the quality is major. And this another representation is the chromogram. It's a 12-dimension one-hot vector. So if a note belongs to this this chord, then this note is set to 1. Otherwise, it is 0. So these are the two representations of a chord. And based on this representation, this is the overview of this method. So we try to extract 3 features of this video. The first is the color features, and the second is the semantic features based on clip, and the third one is the tempo feature. And this tempo features is based on RGBD. And we use this use the color and semantic features to control the chord generation process. And this this tempo information is used to control this melody and accompaniment generation. And finally, for the evaluation, we just we want to design an objective metric for video to music correspondence. And so we just follow the design in text to image, because in text to image generation there are some like clip precision. So in video to music, we think it is similar. So we just try to train this music video clip. Also use contrastive learning, and then try to achieve a similar clip precision in this area. So we use this music video clip as the evaluator. And then we, given this generated music, we try to retrieve some videos from this data set, and we just see the rank of the ground truth of the input video in all of these videos. Like if this video is in the top 1 or top 5 of this data set, then the music is good. So so we also calculate this R precision and median rank. And these are the experiments. This first one is on the SIM-ME dataset, which is the dataset we proposed. And SIM-ME, in the SIM-ME, SIM is for symbolic and MV is for music video. So when we compare this method with this previous CMT and the previous method, we can see that the video to music correspondence and the music quality is better. And we also design some subjective evaluation on the music itself, on the video to music correspondence. And this method can also use for unconditional music generation, that you generate a music from scratch. So we compare it with methods like compound word transformer and music transformer. Yeah. So these are demos of this this news prod model. Oh, that's very short. And the this second one, this is the unconditional music generation by this model. Next is the recent paper called VMB. It's in last year. This is actually in the last year is mirror of the LM for MA workshop, and yeah, it's organized by Yinghao. Yeah. So this method is called multimodal music generation with explicit bridges and retrieval augmentation. In this paper, we define this task as multimodal music generation. So it's not only generating music from videos, but it can also generate music from text and images. So we want this single model to generate music for all of these input modalities. Yeah. So the main problem is that the current methods, they just suffer from the limited data scale and the weak cross-model alignment and the lack of controllability. So our motivation is that we can just design these two cross-model bridges, which is the text bridge and the music bridge, that can improve the alignment and enhance the user control. Let me explain this. It's basically you have this video or image input, and you first convert it into a description of the music. This is text bridge. It's like the description of the music I want to generate, such as this dynamic and emotive soundtrack featuring a rich blend of strings that evoke a sense of adventure, romance, and epic drama. So this is the first part of this model, and the second part is you try to synthesize the music given this text description of the music. So the second part, we can use a pre-trained model like Stable Audio Open or Audio LDM and this kind of models. So basically, if you have this pipeline, you do not need to have this pair data of videos and music. You only need a video to text dataset and a text to music dataset. And also, based on this design, you can also achieve this better comparability because you can directly modify this text, this intermediate representation. That if you want this music to have more instruments, you can just edit this text bridge, and you do not need to regenerate this music from the video. And there's also this music bridge. This is based on this intuition that if a musician tries to compose some music from a video, he may just think of some other suitable music for this video, and he may try to compose some music based on this music, but based on this existing music. So it's like a reference. So this reference is actually RAG or RAG in this method. So you have this music data set, and we try to retrieve some relevant music from this data set, and this retrieved music is used as a reference to generate a better music. So yeah, we also come up with some data sets for this. So the first data set is MTV 24K. MTV just means music, text, and video. So it's like a data set with music, text, video triplets, and it's used for this first part of this model, which is the visual to music description. And the second data set is the MT512K. It's a text to music data set with 500,000 pairs. It's basically used for the foundation of RAG. So this figure below is the collection process of these data sets. We try to collect some music and collect some music videos from these platforms like Spotify and YouTube and other platforms, and we tag this model of their instruments, their genres, and BPM and keys and lyrics, and convert this metadata into a textual description of this music, like this one, an uplifting and catchy pop track blending bass synthesizer drums, which is perfect for nostalgic and fun moments. And then, so we have this data set of videos and this music description. And this table just compares our data set with the previous data sets. It said we have the annotation of genres, of music descriptions, the music attributes. And so for this method, the first part is the text bridge, which is called MMDM. It's a multimodal music description model. So we use this data set to train this model and it can just, it's basically like a video captioning model or image captioning model. Like the input is a video or image and the output is a text. But this output is not a description of this video, but a description of the music you want to generate. So like if this if this video is never gonna give you up, then this music description is like this description below. So that was the text bridge, and the second is the music bridge. It's a dual track retrieval. It has a broad retrieval and a targeted retrieval. So the broad retrieval is based on the music itself. So we just use this inputs, videos or images or text, and use this collapse embeddings to compute the similarity of this input with the music in your database, and try to retrieve the most similar one. And for the targeted research, the criteria is that we want user-defined attributes to be similar, such as the tempo, the genre, the instruments, the mood. And so we try to like retrieve music from this database that has the similar attributes to the user-defined attributes. So we have this two sets of music, one from the broad retrieval and one from the targeted retrieval, and we just integrated into this ECMG module. ECMG is the explicitly conditioned music generation. So it's based on a diffusion transformer. In this case, it's stable audio open, but we add this control former block. This control former block, it has inputs of the retrieved music, and then we try to integrate this music to into this, and also this text bridges into this module to create a high quality and controllable music. So this is experiments. This first table is about the video to music generation on the CMME data set. And this is for the text to music generation. We compare with a method like music gen or audio LDM. And this tool is image to music generation and video to music description generation. These are lots of ablation studies. And we have two demos here. This first demo is about a game video. The second demo is about a documentary. Yeah, so the last part is a very brief discussion on the social impact of video to music. So the first is the impact on this actually the film scoring industry, or like creating soundtrack for films. This is actually, or another paper is doing submission is about the social impacts. So our core idea is that the video to music technologies, for now, they just try to simulate styles and rhythms, but it fails to meet the film soundtrack demands for emotion, context, and coordination. And there are some key barriers, like the disconnected workflows, and also the lack of collaborative feedback. It's like the human in the loop challenge I said before, because for now, like this method only like generate music end to end, and you can only regenerate this music to create a better one. But it's not like the common practice in the film scoring industry, because usually this composer just create a music and refine and refine and refine until it has a very good quality. And the second barrier is the poor cultural context awareness. It's like if this video has some deep context related to culture, such as maybe some Chinese traditional culture or other culture, but these models are not very aware of this latent context. So it is difficult for these current models to realize this. And the third one is the cross-professional communication. It's like for film scoring, basically, it's about a director of the movie tries to like write this. He may write some requirements for this music, and this composer tries to compose some music based on these requirements. But this director is not in this music industry, and he may be not so professional in this area. So there's actually a cross-professional communication. Like this composer needs to understand what this director tries to convey. But this is very difficult for these models to achieve. And also this fourth barrier is the sound balance. Is that if you want to create a background music for these films, it is not played alone. It is played together with the sound effects and human conversations in these films. So actually, the volume cannot be too large, or it may affect the conversation of these people in these films. But it can also not be so the volume cannot be so low that you cannot hear this music. But this is not like considered by these current models. So, and our idea is that we need to involve these technologies need to evolve from a substitute of human composers to an intelligent collaborator of human. So it's like these models can help the human to compose the music instead of compose the music alone. So it's like if a composer tries to compose the music for these films, he can just use this method to first create an initial version of this music. And maybe this music is not cannot be directly used, but it can inspire this human composer. Like, oh, I can use this music. I can define this music as this genre, or maybe I can have this melody. And this is the first function of this model, is to inspire the composer. And the second is to assist. Is that say maybe the composer has composed some music and he wants to refine it, but he doesn't know how to refine it. And he may ask the model that I have this music, and this music has some piano tracks, and I want to generate other tracks like guitar and bass and drums. And can you generate this for me? And he uses this model, and this model can help him to generate a better version of this music. So it's like a distance. And this final page is my personal opinion. Is that I think I consider the function of AI music. I think the AI generated music actually lacks the genuine emotion and subjective expression. It's basically just composed by a machine. So it's very suitable for functional scenarios. Say if you need some music for your short video, or for like for background music in the restaurants or on the street, then you may need some functional pop music, and then you can use AI music, because I think this is the functional scenarios that you do not can't understand the human the emotion or the idea that the composer wants to convey behind this music. But for the other type of music, like this non-functional music, like this indie music, like I may listen to some rock or folk or other types of music. This music, I think they demand the human creativity and ideas. So if this music is composed by a machine, an AI, then I will not listen to this music. And I think most of the people do not listen to this AI composed music. But for film soundtrack introduced in this previous page, it is kind of like a middle ground between these two types. It is functional because it serves the work, serves the movie, the films, but it also allows the composer to convey their own like personal expressions or ideas. Like if you listen to some music genre created by these famous musicians like Hans Zimmer, you may notice there are some typical like styles or some ideas he tries to convey. So this film soundtrack is like a middle ground between this functional and non-functional music. And if I just, I think this is similar to the AI writing. So for AI writing, we may appreciate the AI written like manuals or summaries or like guidebooks, because they are functional and they can help us. But we do not need to like understand the sentiment behind this. But I don't think there are many people that would read human AI written novels or poetry, because it is kind of like we do not think it is very reasonable. Yeah, because the sentiment they try to convey is actually not so expressive. Yeah, and so actually the idea is similar to the previous page, is that AI can serve as a creative assistant, but not a replacement for human expression in this non-functional music. If you want to create a rock music, you directly use this model to create a rock music. This is not so reasonable. But if you use this model to like refine your music or give you some inspiration, then this is very useful. Okay, so this is all of my talk for today. Thank you for listening. And you can check out our repo in this QR code. Yeah, thank you.
Any questions? Any questions online?
So I know this would be a little different topic, but
Yeah.
if I suppose the goal is to edit or rescoring existing music to
Yeah.
be there, then what would be the challenge of that kind of editing of existing music?
You mean you retrieve an existing music and edit it to fit this video?
Yes.
The challenge is that sometimes you want the music, like if the video has some motions, you want the rhythm of the music to align with this video. If you watch some carefully edited videos, such as this vlog, how do I test this? Yeah, like this vlog. The original music in this video is actually a very carefully edited. Like if there's a transition in this video, the music is also has a strong music beat in this. But if you try to create a music based on existing music for this video, actually you cannot edit this music, because if you edit this music, you cut the music into pieces or you delete some bars, the music is not reasonable. So for this video producers, the common practice is to they edit this video instead. They edit this video to fit the music. But this is very difficult and very, very time consuming. So I think this is an advantage of generating the music instead of retrieving music. Yeah.
Have you tried to use LLM as a genre, like Gemini Flow, to evaluate the quality of the music or the alignment between the video and the music?
Actually, we have not tried this kind of model before. Yeah, I think because actually these methods are like for like in the end of 2024, and back then we do not have so strong audio models. I think this is a potential area to explore in the future. Thank you. Oh.